guys, we're back. Let's do more examples for determining the chirality of a molecule. Alright, so on this example we have a decent shaped molecule. We have an alkyne, we got a few alkyl groups coming out of this molecule. And the thing to recognize is that we have a carbon right here that has three things coming out of it. Now technically this one has four in particular, four things coming out of it, but methyl, methyl, and methyl are the same. So this carbon cannot be chiral. This one right here also has three things coming out of it, but two of them are methyl and methyl, so this carbon cannot be chiral. This one on the other hand has isopropyl coming out of it. We have a CH2 with a T-butyl group coming out of it, and we have an alkyne group coming out of it. So this carbon, it's got four different things bound to it. So this carbon is chiral. So technically speaking, that's the first part of the flowchart. We've determined which out of all the carbons happens to be chiral. Now the main premise is to determine whether or not this is an R or S configuration. And in order to do that, we have to assign priorities to all of the groups bound to this carbon. Alright, so what we need to do is first look at what is directly bound to the chiral carbon. And technically speaking, it's all carbons. We have the carbon of the alkyne, the carbon of the isopropyl group, and the carbon of this CH2 group bound to the chiral carbon. So that in and of itself doesn't tell us what's the higher priority group or not. Now, the one thing, of course, that we do know is that the hydrogen that is also bound to the chiral carbon, that is definitely lower in priority than any of these groups because hydrogen only has an atomic mass of 1.0 gram per mole, whereas each one of the carbons is 12 grams per mole. So hydrogen is definitely the lowest priority, no questions asked. But the three carbons, now this is a little ambiguous. They are all the same, so now we need to go forward and further out into the molecules to see if there's a distinction. So what we're going to do is determine what's bound to the carbons adjacent, right? So the carbons directly bound to the chiral center, what is bound to these neighboring carbons? And what we see here is that on this carbon, we have two other carbons bound to it in addition to this hydrogen. Down here, we have two hydrogens and one other carbon bound to it. And for the alkyne, technically speaking, since this is a triple bond to another carbon, technically speaking, you have a total of three uh, bonds to carbon. So three carbon bonds, technically speaking here. For that carbon, you only have two carbons and one hydrogen bound to it. And this carbon here, you have one carbon and two hydrogens bound to it. Now, notice that I'm not accounting for the chiral center because that's common among all three of them. You could definitely include it if you wanted to, in which case this will be three carbons plus one H. This one will be four carbons, and this one will be two carbons and two H's. That's totally fine if you decide to do that. I'm just going based on the idea that, yeah, they all share the same connection to that chiral carbon, so they all will have that extra carbon. So you can include it or not, totally up to you. I'm excluding it in this discussion. So what you basically now tell by looking at the things attached to the neighbors, right, is that you can start seeing some differences. Now, in the case where the groups are regular organic groups, meaning that you have carbon and hydrogen, um, this is going to come down to how many carbons are bound to this neighboring group. And in the case of the red group, we have two carbons bound to the same carbon. Over here, we only have one carbon bound to the carbon in question. And over here, we have three carbons bound to this center. So what that basically tells us is that the alkyne is the highest priority group out of the three. The second priority group, of course, is going to be the one with the second most carbons, which is the red group over here, and the pink group is going to be the lower priority. So we have basically found out that, yes, alkyne is group 1, isopropyl is group 2, and the CH2 group here is group 3. If we draw a half Newman projection for this, and this one is actually perfect perfectly set up because we have the hydrogen exactly pointing to the back. So the view of the molecule is just how you want it, because our point of view is exactly as you see it right now. The red group is going to be pointing up and to the left, the blue group is going to be pointing up and to the right, and the pink group is going to pointing straight down, which is exactly what we have here in the half-Newman projection. So going from priority 1 to priority 2, from priority 2 to priority 3, and priority 3 back to priority 1, we see that we have a counterclockwise rotation. And what this is telling us is that the molecule is got an S configuration. All right, so now that we know that the configuration of the enantiomer at hand is the S rotamer, um, what we're going to now do is name the molecule, right? And in order to do that, you have to include the functional group, which in this case is the alkyne, and you have to determine the longest chain. So if you look at the blue segment that I have here in the molecule, starting from the alkyne, we have the most carbons included if we follow the following pattern. This also ensures that we have the most substituents present on the longest parent chain, two requirements that are needed to come up with the proper parent chain. So altogether we have 6 carbons, 1, 2, 3, 4, 5, 6. So this is a hexane, well, technically a hexane molecule. And sticking out of position 3, we have an isopropyl group. Sticking out of position 5, we have 2 methyl groups. Therefore, the molecule has the name 3 isopropyl 5,5 dimethyl 1 hexane, right? Just to tell us where the alkyne is located in this molecule. And at the front of the entire molecule, we tell that this is the S configuration. I'm even specifying where exactly that S configuration is happening. But technically speaking, since this is the only chiral center in the entire molecule, you could just write parentheses S without the number, and that will still apply. Okay, so this is one of the examples. Let's take a look at another one of similar difficulty. So looking at everything in the molecule, I just made a quick little change. I've added a chlorine to what we had before and removed the methyl group of the isopropyl. So what you once again will see is that this carbon has 4 things coming out of it, but 3 of them are methyl groups, so that's not chiral. This carbon right here has 3 things coming out of it: CH2, C triple bond, and another CH2. Okay, so CH2 right next to it has another CH2. This CH2 has a carbon with no H's. So these 2 groups are definitely different, and the alkyne is different than those 2. The hydrogen that is also bound to the carbon is different. So all 4 groups are different. You got yourself a chiral carbon. So what we need to do now is determine the priorities, and we do it the same way we did before. First, we start by saying, okay, on the chiral carbon, there is a hydrogen bound to it, but then you have 3 other carbons bound to it. What we can say for sure is that the hydrogen is going to be the lowest priority overall. Now it comes down to figuring out what's happening with the carbons. Okay, so we look at what's bound to those neighboring carbons. The carbon over here has another carbon bound to it, and it has 2 hydrogens. The pink carbon right here has 2 hydrogens bound to it and another carbon. And the red carbon here technically is bound to 3 other carbons because of the triple bond. So what we can see is that the alkyne carbon once again has the most connections to carbons. Therefore, this is the first priority. But the blue segment and the pink segment, we don't have a clear cut as to which one is the second priority and which one is the third priority, because they have the same number of carbons, the same number of H's present. What this is telling us is that we're going to have to move further out into those segments to see if we find a difference. But for now, we know that priority 1 is the alkyne group. Priority 4 is the hydrogen that's bound to the chiral center. All right, so now extending further out into these groups means that we're going to look at these carbons, farther out. And the carbon over here on the blue segment has 2 hydrogens bound to it and 1 chlorine bound to it. The carbon over here has 3 other carbons bound to it. Now, when you start looking at heteroatoms, bound to the carbon in question, here you have to be careful not to go and add the total number of molecular weights. That's at all not what you ought to be doing. Sometimes it will work out the same way, but in other instances, it will give you the wrong answer. What you have to basically look for, though, is if you have an atom that by itself has a higher molecular weight than any of the other atoms by themselves. And what that means is that carbon, it doesn't matter if you have 3, 2, or 1, carbon by itself has a molecular weight or an atomic weight of 12. Chlorine by itself has an atomic weight of about 35. So chlorine is automatically heavier than carbon. Doesn't matter how many carbons you have. The fact that this blue segment contains the chlorine and chlorine by itself is heavier than carbon automatically says that the blue segment is gonna be the one with a higher priority. And that's what makes the distinction in this molecule. So priority 2 is the blue segment and priority 3 is the pink segment. And of course, priority 4 is still the hydrogen that's bound to the chiral center. So here, technically speaking, because the bond is dashed, the hydrogen is pointing at you. So if you were to draw your half Newman projection, technically speaking, the way it looks right now, you're looking at it from the opposite point of view. The hydrogen, the lowest priority group, is pointing at you. The red segment is still on the left, on the right side. The blue segment is on the left side, and the pink segment is pointing down. But this is the opposite view that you want. If you look at this thing, the rotation right now looks to be going counterclockwise. It looks like an S configuration. But technically speaking, you have to do the opposite, right? And the reason why is because the lowest priority group is pointing at you. So what you see in terms of rotation is actually the opposite of what's happening, because technically speaking, this needs to be rotated 180 degrees. And when you do that, the red group is technically now sitting on the left side of the molecule. The blue group is sitting on the right side of the molecule. And this is because right now that carbon hydrogen bond on the chiral center is pointing exactly away from you, right? So we are in essence rotated this molecule. But the easiest thing to do is to note that the lowest priority group is pointing at you. So you determine the rotation on your molecule, which looks S, you end up doing the opposite. So if it looks S, it's in fact gonna be R. And then as far as naming, once again, we have the hexane fragment as the longest set of carbons in your parent chain. At position 3, you have an ethyl group that's sticking out, but within that ethyl group, we do have a chlorine that's bound to it. So this is an example of a substituent that itself has a substituent. So it's a substituent within a substituent. At position 5, we still have the two methyls. So what we do to name a substituent with a substituent of its own is to basically give it some new numbering scheme. And specifically, the carbon that's directly bound to the parent chain has the lowest value. So that's priority, not priority, excuse me. This is carbon 1 prime. And we're using the primes now to distinguish it from the numbering of the main chain of the molecule. And the further away we go from the connection to the parent chain, the more we increase the number. So this is 1 prime, that's 2 prime. The chloro group is bound to position 2 prime. So as far as naming this molecule, you will have to do it using parentheses. So this entire group is the 2 prime chloro, 1 prime ethyl. And that entire thing in parentheses has the 3, regular 3, so this is not 3 prime, but regular 3 in front of it to tell us that this entire segment is the functional substituent that's bound to the parent chain. And after that, you have your typical thing, 5,5 dimethyl 1-hexane. So this is just something that you might encounter in the future, so keep an eye out on it. And of course, since we have a chiral center, don't forget to introduce the R assignment in front of the molecule in parentheses. Okay, so that gives us two robust enough examples of how to determine the names and the assignment, the chiral assignment for the enantiomers at hand. In the next video, we're gonna start talking about how we go about measuring how much of an enantiomer we have present in a mixture. So see you in the next video.